Hello, thank you for your coming. It's great to be here again at Big Data Spain. My name is Arkadiuz Jachnik, and today I'm going to talk about Apache Spark versus rest of the big data world. I would be glad to answer any questions at the end of my talk. Let me start with just a few words about myself. I'm from Poznań, from Poland, and today I have the honor to represent the team of Big Data department of Agora company, where I am a data scientist, and currently I'm working on user profiling and recommendation system. Moreover, I am a PhD student at Poznań University of Technology, and my current research activities concern online classification algorithms. Next slide, please. Okay. As I said, I'm a member of a big data team of Agora company. I think the best big data team in Poland. And today we're all here at Big Data Spain, so we're open to answer any questions and exchange of our experience. And today at 5 to 4 p.m., these two guys, David and Bartek, will present on talk about new real-time data processing with NiFi and Spark, so I invite you. As I said, I'm from Agora. Agora is listed one of the biggest Polish media companies. Agora owns a number of leading Polish newspapers and magazines. There are dozens internet portals and services. Agora owns cinemas, televisions, radio stations, publishing and advertising companies, and that's Agora. Today we'll be talking about Apache Spark, well-known open source cluster computing framework. And in Agora, we use Spark everywhere. Spark plays a key role in all layers of our big data platform. And we have over 3 years of experience with Spark framework, so I think we can today share some interesting experiences. Sorry, animations are really slow. Okay, and during development of our Spark applications, we encounter many technical issues at the confluence of Apache Spark and the rest of big data world, Hive, HBase, Kafka, external relational databases like PostgreSQL, MySQL, etc. And in this presentation, I'll try to propose solutions for 5 problems. How to post-process and save several parts of data in parallel. How to load huge amount of data to HBase DB. How to use Spark with JDBC input and user-defined functions. How to extend Hive HBase handler tool, and how to implement own offset store for Spark streaming Kafka integration. I think my talk is particularly relevant to big data engineers and developers. Okay. Point 1 of my presentation deals with our example of processing of data frame parts in parallel. The slide shows a sample of data in Spark data frame we want to process and save to output relational database. There are users of difficult to pronounce Polish names, and you can repeat: Grzegorz, Bożena, Krzysztof, Grażyna. And each user has a set of recommendations of articles with scores. Each recommendation has one of 4 types, type 1, 2, 3, and 4. And what we want to do, we want to save top K recommendations for each user, and recommendation of each type should be written to another, for example, PostgreSQL table. Okay, I prepared a sample Scala code to show 3 approaches. Here I defined our sample data frame and recommendation types. Recommendation type is defined by case class with code name, with number of recommendations, and with name of output table. And this right side of the slide presents expected output of our Spark application. So for each recommendation type, we have users with top K recommendations, and recommendations of each type will be inserted to various tables. In standard approach, for each record type, we have to take data frame with our input data, select rows of current type, and take top K articles for each user by the Spark window function. And at the end, we have to collect post-processed data and save them into an output database. Okay, let's check how it works in Spark. On the slide, you can see the screenshot of Spark job dashboard. There are 5 jobs. Job 0 is an aerial process of data loading with repartitioning and caching. And jobs 1 to 4 are our processes of each of the 4 recommendation types. It can be seen that all jobs are started one by one, but not in parallel. However, 3 last jobs have many skipped tasks. This is because Spark executes full repartition. Because Spark runs a full query plan on the first job with first collect action. In such a way, Spark can skip repartition and cache functions for next 3 jobs. In summary, we have non-parallelized post-processing functions, but the query plan is better optimized. So how to parallelize our post-processing? Okay. We can try to use simple Scala parallel collections. So we can add par function after collection of record types. What has changed in our application run? Something wrong with this remote control. Okay. Now all post-processing functions started simultaneously. Unfortunately, here we have too many tasks, because for each parallel job, Spark runs almost full query plan. Okay, so how to fix it? There is a simple trick. We try to replace for each function on record type collection by our own simple function, Parallelized Processing. It takes 2 parameters as an input, our collection of record types and the function f, which is our post-processing. How it works? It's very simple. It executes function f on the first element of record types, and next it runs rest of the tasks in parallel using Scala parallel collections, as I presented in the previous approach. What is the effect? How it works in Spark? Spark runs job 1 separately. So here Spark can cache data at first collect action. And after job 1, Spark can run last 3 jobs in parallel, skipping most of tasks. Okay. Our experiments have confirmed that for our applications, this is the fastest approach. Okay. In our Spark applications, we use simple library Scala-like JDBC for inserting a small amount of data to PostgreSQL and MySQL. Scala-like JDBC is a simple wrapper on well-known JDBC APIs. To use it, we can just create simple object with a connection pool, and it can be easily used, for example, in Spark for each action. Okay, something wrong with this remote control. Next slide, please. Okay. Thank you. Okay. Let's now move on to the second point of my presentation, fast bulk loading to HBase DB. Apache HBase is non-relational, big table-like database, and it uses HDFS for storage layer. HBase provides simple API where we can insert data with creating put objects, etc. However, this standard approach raises some problems. First of all, it is difficult to integrate with Spark due to complicated parallelization. And for non-presplitted tables, we had problems with wired HBase region something exceptions. And finally, it is slow for millions of data. Our solution is simple, and general idea is that we have to save our RDD data as H files and load them into the given pre-existing HBase table, where H files are HBase files stored on HDFS. Let's assume that our Spark RDD we want to load is a tuple RDD, par RDD, where as the first element we have HBase row key, and the second element of this tuple is of this par is map with data, with array of tuples with column names, cell values, and cell timestamps. Okay, and how to implement such bulk loader? On the slide you can see some code shortcut, but I do not want to go into details because we have no much time today. But I try to show general steps. First of all, prepare HBase connection, HTable object, and region locator. Region locator will help in obtaining start keys of HBase regions for data partitioning. Next, we have to implement our own Spark partitioner for H files. It requires mentioned start keys of the regions and a fraction parameter. Fraction is very important when we want to put huge amount of data, and it is strictly connected with maximum number of H files per region per column family. So the higher the fraction, the better parallelism of H files writing. Unfortunately, I have no time to describe the partitioner code. But the example can be found on the GitHub source, which you can see on the slide. In the next step, we have to prepare partitioned RDD, where we have to split our RDD by column families. And the splitted RDD should be provided to our partitioner. And next, we can save our data by save as new API Hadoop file method. Finally, we can load data to existing HBase table by load incremental H files tool from HBase API. Okay. A couple of things to keep in mind when you implement HBase bulk loader. I mentioned the fraction parameter. It's related to HBase property that you can see on the slide. So remember to set optimal value of this parameter. And next, we recommend to create HBase tables with pre-splits adapted to the format of HBase row key in your table. Okay. In this part of my presentation, I'd like to talk about loading data from PostgreSQL or MySQL to Spark data frame. In Spark SQL, we often use UDFs, user-defined functions. During loading data, for example, from Hive, you can easily use own UDF in SQL query. And now, let's consider loading data to Spark from relational DB. Spark provides simple read JDBC method. The second parameter of this method is, for example, Postgres table name. But here we can put SQL query. But in this query, we cannot use our UDFs. This is because this query is executed by DB engine, not by Spark. Moreover, there is a question how to parallelize this data loading. Okay, let's go back to the first problem, UDFs. To use UDFs, you can simply add Spark column by with column function. And here, by expression, you can we can use our UDFs. But it's still one partition. But we have, but JDBC method has extended version with additional 4 parameters. Column name is our partition column. Next, lower and upper bound are the minimum and maximum values of this partition column. And finally, we have to set number of partitions. What is the effect? On the top left corner of the slide, you can see test data with type column, and this type column we want to use as our partition column. So we expect 4 partitions. And next, we have codes of two Spark applications. And on the right side, you can see screenshots of storage dashboard of Spark. And the first application creates data with 1 partition, and the second one loads data with 4 partitions. So it's very simple. Okay, let's now move on to the 4th point of my presentation, loading data to Spark from HBase through Hive external table. So there are commonly used Hive HBase tool, where with simple Hive query, create table query, we can create Hive view on HBase table. Here we have to set storage to HBase storage handler, and we have to set HBase columns mapping. On the right side, yes, you can see simple example of HBase table and its view in Hive. And in the sample HBase table, there is 1 column family, cities, and columns with Polish city names, and values are some integer values. In Hive view on this HBase table, we have 2 columns, user ID, which corresponds to our HBase row key value, and cities map. It's a map which is mapping of all columns in cities column family. But how to get the last, most recent values? Where are timestamps of our cells in HBase? In our case, we use Hortonworks distribution with HBase 1.1, and in this version of HBase, there is a possibility to add to Hive view the latest timestamp of whole row, latest timestamp from all cells, and yeah, it's sorry, my keynote presentation have been exported to PowerPoint, so sorry for this. Okay, so how to extract timestamps for each row cell? Answer is simple, reimplement Hive HBase handler. But remember, first of all, check your Hive distribution, because your version of Hive may differ from that of the official Hive repository on GitHub. In our case, we found the correct version on Hortonworks repository. Okay. So how to reimplement Hive HBase handler? We were inspired by the patch available on Hive Jira. Unfortunately, this patch has not been reviewed and merged for over 3 years. Okay, next slide. But unfortunately, there is a lot of code. But I have some tips on how to reimplement Hive HBase handler. Functions of parsing columns of HBase column mapping parameter is located in HBase 30 Java. This class produces column mappings objects, storing mappings of HBase fields to Hive columns. Next, lazy HBase row class stores data from HBase row. And here timestamps of processed HBase cells can be read from loaded rows by scanner HBase scanner in lazy HBase cell map class. Finally, parser of columns and HBase scanner are initialized in HBase storage handler Java class. Okay, and the last point of my presentation is about Spark Kafka integration with own offset store, own offset manager. Spark streaming provides powerful stream processing of live data streams, and Apache Kafka is a well-known distributed streaming platform. So what is the problem here? Spark output operations are at least once. So if you want to equivalent of exactly one semantics, you must either store offsets after an independent output or store offsets in an atomic transaction alongside output. There are several options for storing Kafka offsets for Spark. For example, checkpoints, but here we cannot recover checkpoint if application code has changed. Or we can implement our own offset store with exactly once semantics if we want full control and security. Okay, some code with Spark streaming. First of all, we have to initialize Spark streaming context and, of course, our stream. And next, during stream processing, for each RDD, we have to process our data, save them to output DB, and finally we can store our offsets in our store manager. Okay. It's time for some more details. We will implement Zookeeper offset store here. The data stream will be created by the Kafka stream method. Where is my method? Okay, here you are. As an input, it takes name of Kafka topic, Zookeeper path. I will explain it later. Spark streaming context, object of our offset store, and some Kafka connection parameters. In this method, the offset store can return some offsets if our streaming app was running irreal, or it can return null if it is, for example, first run of our application or the topic. In these two situations, we need to initialize the stream in slightly different ways. Okay, and how to implement Zookeeper offset store? In Zookeeper, we store offsets in something like key value format, and the key is some Zookeeper path, and value can contain some parsed string of our offsets. The code of Zookeeper offset store is simple. First of all, in the class, we have to initialize Zookeeper utils with Zookeeper connection. Next, we have to implement save offsets function, where first of all we have to read offsets from RDD, and by this has offset ranges interface, we can obtain offset ranges array of offset ranges with all offsets, all processed offsets of our RDD. And next we can process this data these offsets and save them to Zookeeper by update persistent path method. How to implement reading offsets? First of all, we have to read data from Zookeeper by Zookeeper utils object. And next, if in Zookeeper there were any offsets, we can parse them. And finally, we have to create topic partition objects where we have to store topic name and topic name and partition number, of course. And finally, this method read offsets should return map of this topic partition objects with values of our offsets. And that's all. Thank you.